In this lecture, we are going to explore yet another machine learning model, this time from unsupervised learning. As you recall, one of our main tasks in this section is that of density estimation. That's just a fancy way of saying we're trying to figure out the probability distribution of the returns. So far, we've discovered that the returns are heavy-tailed and that a single Gaussian is not good enough to capture this phenomenon. We then looked at the t-distribution as a possible solution. In this lecture, we will return to the Gaussian. This lecture is all about a technique called mixture of Gaussians, or the Gaussian mixture model. You can tell it's a technique from machine learning because it uses the term Gaussian rather than the term normal. As you recall, these both refer to the same kind of distribution. In this lecture, I'm going to first describe what the Gaussian mixture is and how it works. Then we'll discuss why it works for modeling returns. So, what is a Gaussian mixture? Although we'll be using the Gaussian mixture for density estimation, it can also be understood in terms of clustering. As you may recall, clustering is an unsupervised machine learning technique. The basic idea is this. Suppose I have a dataset. Perhaps I've gathered data on all the students in my class. There are test scores on several tests. Let's suppose my class has 2 tests, so I can plot these test scores on a 2-dimensional scatter plot. When I look at this plot, I'll be able to see some patterns. For example, in the upper right corner, I'll see students who performed well on both tests. In the bottom left corner, I'll see students who performed poorly on both tests. In the upper left corner, I'll see students who performed poorly on test 1, but performed well on test 2. In the bottom right corner, I'll see students who performed well on test 1, but poorly on test 2. These clusters might help me decide how to best assist my students in studying for their final exam. Perhaps the students in the upper right corner don't need any assistance, they are doing just fine. Perhaps the students in the bottom left corner need the most assistance, they haven't performed well on any test. Perhaps the students in the upper left corner slacked off at the beginning of the course, but now they are on track to ace the exam. And perhaps the students in the bottom right corner started off doing well, but some life event caused them to not study as hard later in the course. So what does a Gaussian mixture model do? Well, the Gaussian mixture model assumes that each of these clusters takes on the shape of a Gaussian. As you can see, this allows for a much more expressive estimate of the density of the data. When you see multiple humps like this, it's called a multimodal distribution. It's clear that a single Gaussian or a single T would not be able to capture these details. In terms of clustering, we can take a data point and ask our Gaussian mixture model, which of these Gaussians does that data point belong to? So, using a concrete example, I can take my students' 2 test scores, plug them into my model, and my model will tell me, does this student belong in cluster 1, 2, 3, or 4? So, what does a Gaussian mixture model look like mathematically? In fact, it's just the weighted sum of individual Gaussian PDFs. We usually denote these weights with the symbol pi. Note that all the pi's have to sum to 1, since in order to be a valid distribution, the entire thing must integrate to 1. We already know that each individual Gaussian integrates to 1, and therefore it's easy to show algebraically that all the pi's must also sum to 1. At this point, you might ask, how do we know what each of the pi's are? And furthermore, how do we know what the means and variances of each Gaussian should be? Finding these parameters is called learning. So in machine learning, the act of finding these parameters is what learning entails. Luckily, the math behind the learning algorithm is quite complicated, and again, that itself takes an entire course to discuss, so it will be considered outside the scope of this course. If you're interested, basically just know that it's the same old story. What we want to do is maximum likelihood estimation. That is, we want to maximize the likelihood of the data with respect to the model parameters. We can accomplish this by using algorithms such as expectation maximization. In code, it's a simpler story. We can use the scikit-learn API with all the usual functions. First, we create an instance of the model. Then we fit the model to the data by calling the fit function. Note that because this is unsupervised learning, there is no target, and the fit function only accepts as input the data x. If you want to know which cluster a set of data points x belongs to, you can call the predict function, which will return those cluster identities. At this point, you must be wondering, what is the point of using a Gaussian mixture, which is clearly for multimodal distributions, on stock returns, which have not looked multimodal so far? Well, this may be surprising, but the purpose of using the Gaussian mixture is not for its ability to model multimodal distributions. Instead, it's for a less well-known property, which is that Gaussian mixtures have heavier tails than single Gaussians. In fact, it's possible to demonstrate this algebraically. Pick any Gaussian with arbitrary mean mu and variance sigma squared. Then, suppose I have a Gaussian mixture, pi times Gaussian 1 plus 1 minus pi times Gaussian 2. Gaussian 1 has mean mu and variance sigma 1 squared. Gaussian 2 has mean mu and variance sigma 2 squared. Sigma 1 and sigma 2 can be set such that the variance of the mixture model overall has the same variance as the original sigma squared. It's possible to show that the kurtosis of the Gaussian mixture is larger than the kurtosis of the single Gaussian. For us, we'll simply demonstrate numerically that this is the case using Python. Although as an exercise, you might want to try this yourself on paper.